So first one is the prime factorization, okay? So we want to break down the numbers into factors of prime, okay? Factors of prime, that's why it's called the prime factorization. And the use of that is we can use it to check if the number is a perfect square or perfect cube, okay? And we can also use the same thing to help us find GCF and LCM, okay? So I'll be just demonstrating several examples and then ask you guys to answer a few questions, right? So 56, okay, we'll start with 56. Right, so I want to break this down into factors of primes. So the way I do it is I draw a little box and I use prime number to divide, okay? Just like the way when we try to simplify the radicals, right? We use prime to find the factors. So we can start with 2. 56 divided by 2, 28, right? Divide by 2 again, 14. Divide by 2, 7, right? So the prime factors, prime factorization is 2 to the cube, right? Because 2 times 2 times 2 times 7. That's all, okay? So this part is called prime factorization. Okay, so or you can call it the product of prime factors. Okay, so let's pick 2 questions to work on. All right, it's just questions C and D, the one that's bigger, right? So at the end, use exponents, right? There will be several numbers that are the same, right? For the prime, so you just write 2 to the something, right? 2 to the 5, 2 to the cube, okay? All right, so when you finish factoring C and D, you can raise your hand. All right, so let's check question C first. Okay, Colin, what's your prime factorization?
2 to the power of 5 times 7 squared.
Okay, so you get 5 2s, right? So 2 divided by 2, 784. Divide by 2, 392. 2 again, 196. 2 again, 98. 2 again, 49. Oops, no more space. And then we can divide by 2 again. Not 2 again, 7, right? 2, 7. So total, you get 5 2s and 2 7s. Okay, Eric, what about D? What's your prime factors?
2 squared times 3 squared times 5 times 7.
Times 5 times 7. Okay, so divide by 2, 630. 2 again, 3, 1, 5. And then we can do 3, 105, 3, 35, and 5, 7. Okay, so now you know how to do the factoring, right? Breaking down. We can use it to check if the number given is a perfect square or perfect cube. Okay, so first you need to understand what's a perfect square. Okay, so go back to the top. We'll write some notes there, okay? An example of a perfect square number will be what? Yosher, can you give me an example of perfect square?
4.
4, sure, that's a small one, right? So 4 is a perfect square because 4 can be written as something square, right? We can write it as 2 square, right? Can you give us a bigger one that's a perfect square, Brennan?
169.
Okay, 169. Because 169 can become what?
13 times squared.
Yeah, 13 times 13, right? 13 squared. So as long as I can write it as something squared, then you know it will be a perfect square. Okay, so by breaking it down into primes, then we can see if it's possible to make it into something square. Okay, so that's for checking perfect square. So if I want to check for perfect cube, the same idea. Perfect cube. Nathan, can you give us an example of a perfect cube?
Perfect cube, something like 8, which is like 2 times 2 times 2.
Very good. Okay, so 8, I can write it as a 2 cube, right? So 2 cube. So we need to have something square or something cube. So for example, right, let's say I want to do 324, right? We'll go back to the bottom now. Okay, so we want to show whether the number is a perfect square or perfect cube without using calculator, right? Of course, you use calculator, you just try to square root it, right? So let's say if I want to do it without it. So first I need to break it down, 324, right? So Eric, how do you divide this one into primes? What number do you divide?
2.
So becomes 100 and
62.
very good, go on.
And then you do another 2, which is 81.
Yeah, and then?
And then you divide by 3, so it's 27. And then 3, which is 9.
Yeah.
And then it's 3, which is 3. So that's it.
Very good. Okay, so 324, I can write it as 2 squared times 3 to the 4. I want to see if it's possible to make it into something square or something cube. Right? So what we can do is we look at the exponents now. Because both of them are divisible by 2, right? So I can sort of take out the exponent from each, right? Because remember, when you have exponent on the outside, let's say we have 5 squared to the cube, I can write it as 5 to the 6, right? I can multiply. So of course I can go from 6 and then break it apart into 2 times 3, okay? So I'm going backwards. I want to break apart the exponent. So because they are both divisible by 2, so I can write it as 2 to the 1, because 2 divided by 2, right? Times 3 to the 2, because 4 divided by 2. So that means I have taken out a 2 on the outside. If I multiply n, right, it will go back to the same thing. Okay, so because I rewrite it as something squared, right, something squared, it's possible, right? So I know this one is a perfect square. Perfect square. Okay, now for the perfect cube. Because 2 and 4, they are not divisible by 3. So it's impossible, right? I cannot have a 3 outside and an exponent on the inside, right? 2 cannot be divided by 3, 4 cannot be divided by 3, so it's not a perfect cube. Okay, so I would like you to try the next 2 questions here. Okay, question B and C, to check if it's a perfect square or perfect cube, or maybe it's none, right? Or maybe it's both. All right, so please do question B and C right now. So first I will need to get the prime factors. Okay, what kind of prime factors you used. And then I will need to know whether it's a perfect square, right, or a perfect cube. Okay, so I need to know what goes inside. So that way I would know whether, right, you are not using just the calculator, right, to square root it or cube root it. So you need to find the factors. All right, so let's check. For question B, what are the prime factors? Brennan?
It's
2 to
2 to
the
the power of 9.
2 to the 9. Okay.
Yeah.
Right, so if it's 2 to the 9, Yosher, would it be perfect square or perfect cube?
Perfect cube.
Okay, perfect cube. Then what's inside the bracket?
2 to the power 3.
Yes, very good. And then outside you have a 3, right? So we can do that. Perfect square is impossible, right? 9 cannot be divided by 2. So this is a perfect cube. Right, and Nathan, did you find the prime factors for 729?
Yeah, it's 3 to the power of 6.
Okay, 3 to the power of 6. So do you think it's a perfect square or a cube?
Perfect square.
Okay, how would you do that? What's inside the
If
bracket?
you divide it by 2, but it's also a perfect cube as well.
So inside the perfect square will be 3 to the
3 to the 3.
And perfect cube?
3 to the 2.
Yeah, so this one is both, right? So 729 will be the same as 27 squared, right? 3 to the 3 is 27. Or you can write it as 9 to the cube, because 3 squared is 9, right? So this one is both. Okay, so you can use the same idea, right, to check if it's a perfect square or perfect cube, okay, as long as you know the prime factors. Okay, so prime factor, they are like little molecules that makes up the objects, right? So breaking down, look at it's like looking through the microscope, right, to see what's making up the numbers. Right, so following questions are similar. Okay, we're gonna skip that. Go to, I want to talk about GCF and LCM. Okay, so let's go to page 4. So another use of the prime factorization is to find the GCF of the numbers, right? So look at page 2, right? So number 7, we can use it to find perfect square, perfect cube. Number 8 and 9, LCM and GCF. So the rule to do that, first, let's break it down, okay? GCF stands for what? Does anyone remember? Eric, what's GCF stands for?
Greatest common factor.
Yeah, very good. Okay, so let's write that down first. Okay, so first thing I would like you guys to find the prime factors first, okay, for each one of them. For 24, for 32, and 40. Okay, and once you finish that, you can raise your hand. Okay, so from the chart, right, from the stair here, we can see all the factors, right? So greatest common, right? We want to look for all the common factors. Those 2 and the 3 and the 5, those are the factors, but we want something that they all have in common, right? So 2, of course, they all have, so I circle it, right? So 2 works. So we can write the 2 down. And then they also have 2, right? So that's another 2. Okay? And we can also find another 2 from each one of them. Now I want to get the 3, right? Because the first one has the 3, but then the other one doesn't. Then it's not common. Okay? And also the 5, no more 5 for everyone. Right? So the most, right? Greatest means the most. The most you can get out from all 3 of them at the same time is 2 times 2 times 2. Right? So our GCF will be 2 to the cube. Okay? Which is 8. So you can do the chart like this. Okay? Then you can see what's the most, right? Greatest common factors, you can get it out from each one of them at the same time. Okay? So this is one way to do it. Do it separately. But for GCF, we could also put all 3 numbers at the same time, okay? to save space. So you could divide everything by 2, right? So you're dividing all 3 numbers at the same time, and you will stop until there's no more common number to divide, right? No more common primes. So 2 will work again. Did I divide it wrong? Does 2 work? What did I miss? 2, 24, 32, 40.
It's supposed to be 12, not 14.
Oh, yeah. Thank you. Good eye, okay? You're having hawk eye. Okay. 12 and then 6. Okay. So 2, 3, 4, 5. All right. So you just pick the numbers on the left side. Everything on the left side, that's the common factors. So that also gives you the 8. Okay. So let's fill in the rule for this, right? So GCF, you divide until no more let me see. Yeah, okay, yeah. See you, Colin.
Okay, bye-bye.
Yeah, so you just follow the link, okay, on Monday. Okay, so divide until no more common primes. Okay, prime factor. Okay, so keep dividing until you cannot find anything common to divide. So let's look at the rule for LCM, okay? It's the same set of numbers. This time, because we already factored it, right? So we can just use the same result. I'll write list out, okay? 24 equals to 2 cubed times 3, right? And then 32 is 2 to the 5, okay? And then 20 will be 2 cubed times 5. Okay, so I'll let you guys write down the notes first. And please raise your hand when you finish writing here.
Oh, Jason,
Yeah, you sure?
is the 2q times 5 for 40?
40. Yeah. Sorry. Okay. Yes, should be 40. Thank you. So, okay, but then the question is 20, right? Okay, let's use 20 then, okay? Never mind. I thought the questions are the same. So we should be doing 20, okay? So 20 will be what? 2 times 2 times 5, right? So 2 squared times 5. All right, so write this down and raise your hand. Okay, Eric and Nathan, are you done?
I'm almost done.
Okay. Got it? Yeah, okay. So LCM, what's the LCM stand for, Nathan?
Lowest common multiple.
Yeah, lowest common multiple. So we need to review the word multiple again, right? We mentioned that at the beginning. We have multiples and factors. right? This is on page 1. Multiple includes the factors, and factors are the things that makes up the multiple, right? So multiples usually could be bigger or the same, right? So we are looking for multiples that includes, right? Includes all these factors. These are called factors, but we want the lowest possible to include all of them. So our LCM, you just pick from the list, right? For example, I need to have the 2, right? For sure, there's a 2 as a factor. We also need to have the 3. We don't need to have the 5, right? By looking at the list, we know these are the elements. But then now the problem is we need to figure out the exponent for each one, right? To have enough to include all of them, okay? So if you look at the first one, let me erase that. Right, you look at the first one, the exponent has a 3, right? So we need to have 2 cubed for sure. But then if you look at the second one, it has a 5. Then 2 cubed won't be enough to include that. So I need to increase, turning into 5. So inside 2 to the 5, I still has the 2 to the cube, right? 2 to the 5 means 2, 2, 2, 2, 2, right? So it also has 3 2s as well inside. So it's okay, right? And also, it also includes 2 2s. So it's big enough, right? We want the least possible, right? So 2 to the 5 is still a multiple of 2 to the 2. Now from the third one, we also need a 5, right? So we just need 1 5. So 1 5, 1 3, 1 3, right? So inside this, you can find all 3 of the factors. Okay, all 3 of them are part of the LCM. Okay, so you do not need to add up all the exponent for the 2. You just pick the lowest possible that's included, that can include all the 2s. Okay, so that's one way to do this, or you could also use the chart, right? Use the chart, you can do all 3 together. So let's say 24, 32, 20, right? Suppose I don't want to find out each factor separately. So I do the dividing as well, okay? So I start with 2, the prime. So 12, 16, and 10. I can do another prime again. So 2, 6, 8, and 5. Now, no more common GCF now, right? So if we are looking for GCF, then that's it. GCF will be 2 times 2. But because we are not looking for GCF, we are looking for LCM, we want to break it down as far as we can, okay? So for 6, 8, and 5, I can still divide the 6 and 8 by a prime. So I'm gonna do that, okay? So 2, 3, and 4. The 5 doesn't work, it's okay. We just drop it down, okay? So this one, you drop it down. Now 3 and 4 and 5, because the 4 is still not a prime, so I'm going to divide again. Divide by prime. The 3 is already a prime, so you just drop it down. It doesn't work. Drop it down. And then 4 will become 2. 5 is a prime, so I just keep dropping it. Right? So you will stop until the final line. Okay? Until they are different prime numbers, or you see 1, okay, or 1. right? Because if you have two prime number, let's say you have 2 and 2 at the very last line, then you can still divide by 2, then make the bottom number 1 and 1, right? So you divide until the very last line become different prime numbers, or you see ones at the bottom, okay? So now because I see the bottom, we have 3 and 2 and 5, right? They are all different primes, then you can stop there. So our GCF will be all the yellow highlighted, 2, 2, 2, 2, 2, right? 5 twos and the 3 and the 5. Okay, so that will be the rule for finding LCM, okay? So you will divide, compare with the rule for GCF, okay? So this one you divide until last line has different primes or 1. Okay, so please raise your hand if you finish writing this part. Okay, last bit of the notes is to talk about the system, okay, where we group all the numbers together. So all the numbers that you know, whether it's decimal, fractions, square roots, right, radical, exponents, fractions, did I say that already? Okay, they are all called real numbers. So real number is like the mother, right, the very beginning, the root of everything. So use the R, okay? So this here you see is a tree diagram. So first it will divide into 2 groups. One is the Q, one is the Q with the bar on the top. Q represents the rational numbers. Okay, and Q with the bar, which means it will mean the not irrational, right? Not rational means irrational numbers. Right, so please fill into the blank. Rational numbers are numbers that can be, look at the top, right, can be written in the form of fraction, okay? So it can become a fraction. Irrational means it cannot become a fraction, cannot be rewritten as fraction. So let's start with the irrational first, okay? Some of the common irrational numbers. Aaron, do you know? What numbers will be categorized as irrational? Aaron? Did you say something?
Wait, root 5.
Root 5, okay, yeah. So root 5. Did you see the example? Okay, so root 5, because it's the decimal, if you type into calculator, it will go on forever, right? So that's why it doesn't belong to a fraction. Something like pi, right? Pi, it doesn't have a pattern, okay? Something random, right? Even though it will be sort of like a pattern, but it doesn't repeat, okay? So 0.321, random, right? 5, 7, 8, blah, 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 okay? So the definition for be that a decimal that does not repeat and does not end. Okay, doesn't have a repeating decimal, right? So something like 0.1111, right? Then that one is still rational. Okay, So does not repeat and does not end. Okay, and then, so everything other than that, it will belong to rational. So inside the rational, we have something we already covered at the beginning, right? We have the integer, which is the I. So including the negative side and the positive side and the 0, right? And whole number, does anyone still remember? Nathan, what's whole number?
Whole numbers are like a 0, 1, 2, 3, 4, 5, 6.
Very good.
You
So
know.
starting from 0, right? So it'll be whole number. So it's part of the integers. So start from 0, 1, 2, 3. Inside the whole number, we have a smaller group called the natural. So it starts from 1, 2, 3. Everything other than that will be the negative integer. Okay, so that's the integer part. That doesn't have decimal. If you have decimal, it could be terminating decimal. Terminate means stops, okay? Ends. Terminating decimals. So something like 2.5, right? 2.5, you can easily write it as a fraction, okay? So if it's terminating, it will be rational numbers. And repeating decimals. So like 0.3 repeats, 0.333, so on. This one can be written as 1/3. Okay, so any repeating decimal can become a fraction. And then, of course, the final one will be the one that are already a fraction, right? So for sure, they are rational numbers. So like 2/3, those are rational numbers. Okay, so you need to just know the different category of the numbers. All these makes up the real number system. Okay, can you raise your hand when you finish writing this table, the tree? Okay, yeah, good. So basically it covers the basic of this chapter. There's not too much question to ask, okay? Basically, if you understand the tree and then you just refer to this, you can answer the most of the questions. So you will still get a homework, even though I will still mark it, even though I won't be seeing you, some of you, okay? But then you can still get it back, okay? And those of you are participating in the summer, please stay after class and we'll just check out the link, okay? And then other than that, then you guys can have a good summer, okay? If you're not doing the summer class, okay? Probably I'll see you again in the future, okay?
Thank you, Jason.
Yeah,
See you
you're
next year.
welcome. Yeah, see you next year.
Bye, Jason.
Bye, Eric. Okay, so Yosher, Sarah, Aaron, and Brendan, right? So you guys can go to Google Classroom, and then I'm gonna open up the other Zoom, okay? And I'll see you there. Okay, I will close this one now.